All right, so mirrors. So we're first going to go through the vocabulary that you have to know to do mirror problems, and then as this lecture goes on, we'll use these terms, and it'll make more sense. So going down the list, object distance. The object distance is simply the distance from the object. So in this diagram, here's your object, here's the mirror. That's a concave mirror, kind of like the inside of a spoon, the concave side of a spoon, for example. So object distance is the distance from the object to the mirror. SO, object distance. Image distance. Now, mirrors form images. The distance from the image, so this guy right here represents the image. The distance from the image to the mirror is image distance, SI. Okay, principal axis is this line that goes directly into the center of the mirror. And it's not the ground. I've heard that question many times. It's not like this mirror is buried under the earth. The reason why you want the principal axis going into the center of the mirror is so that allows for inverted images. Notice that this image right here is opposite of the object. It points the other way, meaning that it's upside down. Okay? So principal axis is this reference line that goes directly into the center of the mirror. Okay, magnification. Magnification, there's an equation for it. You're going to be calculating magnification, but magnification tells us how big the image will be. Okay, so for example, if your magnification is equal to 1, what that's telling you is the object and the image are the same size, which is not the case on this diagram. If you look here, so here's the object, here's the image. Which one is bigger by far? The object. The image is smaller. This would be a magnification, just to ballpark it, for this diagram here, this would be a magnification of about 1/3. So what does a magnification of 1/3 tell us? The image will be 1/3 the size of the object. Okay? What would it mean if you had a magnification of 2? If you had a magnification of 2, what would that be telling you? The image is twice the size of the object. Okay? Now there's also a sign convention for magnification, which we'll get to. If your magnification is positive, that means the image is upright. If your magnification is negative, like it is right here, so for this situation, this would actually be a magnification of negative 1/3. If your magnification comes out negative, negative for a magnification means inverted. Okay, but we'll talk about that on the next screen. Okay, center of curvature. Now look, these mirrors here, they're referred to as spherical mirrors. So see this right here, see our mirror? We call this a spherical mirror because it's like it came from a sphere. Can you imagine that? Like we just extend that circle, right? Would this circle have a center? Yep, it's right here. Well, close enough. Okay, this center is referred to as the center of curvature, okay, for a spherical mirror. Now, would this circle have a radius? Yes, it would. That radius is called the radius of curvature, indicated with a capital R. Okay, half the radius of curvature, if you take exactly half the radius of curvature, that's referred to as the focal length, indicated with a lowercase f, focal length. And then the point that corresponds to the focal length is called the focal point. It's a point. And the focal point is directly between the center of curvature and the mirror. So those are the terms. Simple as that. All right, now let's go to the next screen. You know, real quickly before we go to spherical mirrors, the AP exam, they've asked about plane mirrors or flat mirrors, like your bathroom mirror. When you look at yourself in a flat mirror, there are certain things that are always true, and I've seen this on multiple choice exams. So first thing, object distance equals image distance. So here's the object, here's the image. Oops, didn't want to do that. Okay, here's the object, here's the image. So the object distance is SO, the image distance is SI. For a flat mirror, these distances are always the same. So it's going to be a simple question, something like this. If you're standing 5 feet in front of a flat mirror, how far will you be from your image? 10 feet. Because if this is 5 feet right here, if that's 5 feet right there, then this is going to be 5 feet, which means the total distance between object and image is 10 feet. Okay? All right. Second thing, image will always be upright. So see this image right here? It's never going to be flipped upside down for a flat mirror. Virtual. Guys, for right now, I'm going to leave this term alone because I'm going to define it later. When I explain ray diagrams, I'll talk about what virtual means. So for now, just make it's virtual. I'll explain that later. And not magnified. What does not magnified mean? M equals 1. M equals 1, that indicates object size and image size are exactly the same. If you multiply something by 1, it stays the same. And then right-left reversal. You probably know this. If you're holding something in your right hand and you look in a flat mirror, the image of yourself will have the object in its left hand. Flat mirrors do right-left reversal. Okay, equations. All right, so here are the equations that you're going to be using to solve mirror problems. So the first equation, this is like the first two equations are the ones you're going to really be using. This third equation, we talked about it already. What's the third equation telling us? The focal length is half the radius of curvature. So if you look at this diagram here, so here's your circle, extend the spherical mirror. Here's the radius of curvature. The focal length is half the radius of curvature. That's the third equation. Okay, the first equation says 1 over the image distance plus 1 over the object distance will be equal to 1 over the focal length. Okay? Second equation, magnification. So there's two equations here for magnification. So the two equations, this one is kind of like no duh. You're not going to really be using this, okay? The one you're going to be using is this second one right here. This is the one you're going to be using. Because look, what if you have an object that's 6 feet tall and the image is also 6 feet tall? If you have a 6 foot tall object, so HO would be 6, and the image is 6 feet, what's going to be the magnification of that? A 6 foot object produces a 6 foot image. The magnification would be what? 1. 6 over 6 is 1. Okay? So you'll be using negative image distance over object distance. That's going to be the one that's important. All right, now, I want to point out sign conventions. That's what's going to make this challenging. Anybody could plug into these equations, but unless you know the sign conventions, you're not going to get it correct. Now, guys, I want to draw your attention to something. I'm going to put a box around this. There's a way that we can summarize. See that box I just put there? There's a way that we could summarize the sign convention for these three terms. For object distance, image distance, and focal length. What's the easiest way to remember it? It's super duper duper easy. Front side is plus, back side is minus. See this right here? In front is plus for these variables. Object distance, front is plus. Image distance, front is plus. Focal length, front is plus. And then for all of them, back is minus. Okay? And pretty much your object distance will always be positive. Does it make any sense to put an object behind a mirror? stick an object like behind your bathroom mirror, what's going to happen? Nothing. Your object distance will always be positive. Okay? Now, magnification has its own sign convention right here. Magnification and image height. So the sign convention for this, if your magnification, if you're working with this equation right here, if you're working with this equation and m comes out positive, if your m comes out positive, what is that telling you about the image? It's upright. And you know what? The College Board uses the term erect. We'll just say upright. Okay, if you're using this calculation and m comes out minus, what does that tell you? The image will be inverted. It'll be upside down. Dudes, the sign convention for this equation and the sign convention for this equation, they're different sign conventions. What's the sign convention for this equation? Front side plus, back side minus. What's the sign convention for this equation? Plus is upright, negative is inverted. Okay? All right, now, as we've said, spherical mirrors, we call them spherical because it's like they came from a sphere. There's two types of spherical mirrors. We have what's called concave mirrors. That'd be like this diagram here, you know, where it's the shiny side is on the concave. And then we have convex mirrors, where the shiny side is on the other side, where the shiny side is convex. Now, for concave mirrors, the focal length is positive. Who can tell me why the focal length is positive for a concave mirror? Where does the focal length sit for a concave mirror? So here's your sphere. Okay, the mirror, like, could just complete the circle. There's the center. Here's the radius of curvature. There's the focal length. Where is the focal length for a concave mirror? In front or in back? In front. What's the sign convention here? Front side plus. Now look at a convex mirror. Here's the sphere. Complete the circle. Center of curvature. Here's the radius of curvature. Half of that is the focal length. Where does the focal length sit for a convex mirror? In back. So you have to make the focal length negative. Convex mirrors have a negative focal length. Now, one thing I want to add here, another name for concave mirrors is converging mirrors. Now, the reason for this, and guys, if we had more time, if it wasn't like, you know, the week before AP exams, I'd pull out my stuff, and I got demos for this, but you're just going to take my word for it. Look at, the reason these are also called converging mirrors is if you have parallel light rays, which would be like light rays that come from a distant source, if parallel light rays strike this mirror, so these light rays come in from a distant source, so these arrows represent light rays. What will these light rays do after reflecting off the mirror? They will converge, and they actually converge to the focal point. That's one characteristic of the focal point. Parallel light rays from a distant source will converge to the focal point. Now, convex mirrors, another name for a convex mirror is diverging mirrors. And the reason we call them diverging is if you have parallel light rays, what will those parallel light rays do when they hit the mirror? They will diverge. And guess what? They diverge in a way so that they trace back to the focal point. See this? They trace back to the focal point like that. All right, so let's try a problem here. Okay, so a 6-foot object, and guys, you do not have to convert this unit here. So it says right here, a 6-foot object. You can just leave that in feet. That's giving you the height of this object here, right here. The height of the object is 6 feet. Is placed 1 meter in front of a convex mirror. So this distance right here is 1 meter. The focal length is 50 centimeters, which is half a meter. So from focal point over to the mirror, that distance there is 0.5 meters. So what we're solving for is where the image will appear, the magnification of the image, size of the image, is it upright or inverted. So take like 5 minutes, see if you can solve it. Do this problem. So, hey, I recommend summarize your data. Go like this. Just list everything out. Object distance, image distance, what else? Focal length. You're not going to use radius of curvature, but let's just put it in here. I want you to know it, because that could be like an easy multiple choice question. If they give you the focal length, the radius of curvature is just double whatever the focal length is. What else? Magnification. What are we missing? Object distance, image distance. Let's fill it in. Oh, yeah. H, height of the object, height of the image. Okay, object distance is what? 1 meter, positive. Why did I put positive? What does positive mean for object distance? In front. These three guys right here have the same sign convention. Positive is front, negative is back. Okay? Image distance is a question mark. We don't know where the image will be yet. Focal length is negative 50 centimeters. You got to be paying attention here. This is a convex mirror. Where is the focal length for this mirror? In front or in back? It's in back, so it's minus, right? You got to make it negative. Okay, radius of curvature is just double the focal length. That'd be negative 100. Radius of curvature is double. Magnification, question mark. Height of the object, 6 feet. Height of the image, question mark. Now, look, the rest of this is just algebra. Okay, so finding where the image will be, we use this equation. 1 over SO plus 1 over SI equals 1 over the focal length. So 1 over SI equals 1 over F minus 1 over SO. Then you just plug in. But you got to pay attention to your sign conventions. Oh, look, we got to make these units work. See, meter and centimeter, right? So let's just make this negative 0.5 meter minus 1 over 1 meter. So you do the algebra. 1 over SI comes out as negative 2 minus 1. What's negative 2 minus 1? Negative 3. So this is equal to negative 3. So SI, the image distance, comes out as negative 1/3 meter, or in other words, we'll put it in decimal form, negative 0.3 repeating meters, or 33 centimeters. Okay, dudes, what does this negative tell us? The fact that our image distance came out negative is huge. What is that telling us? The image will be where? In back. It'll be behind the mirror. Okay? All right, next question. Magnification. So we're going to use magnification equals negative SI over SO. So magnification, negative times negative 1/3. The image distance was negative 1/3 meter. The object distance was 1 meter. These negatives cancel. The meters cancel. And we get a magnification of positive 1/3. What does that positive tell us? A positive magnification tells us what? The image will be upright, not flipped. It'll be upright. You guys got it? It's pretty easy. Okay? And then size of the image. To figure out the size of the image, you just use your common sense. HI over HO. Look, hey, the magnification is 1/3. The object height is 6 feet. What's 1/3 of 6 feet? 2 feet. It's going to be 2 feet tall. Or you could take this version of the magnification equation. The height of the image will be magnification times the height of the object. Okay, magnification was 1/3. Height of the object, 6 feet. The image will be 2 feet tall.